Assalamu alaikum. So let's go on and talk about enzyme kinetics. So for any chemical reaction, there is what is known as kinetics, which basically describes rates or how fast a chemical reaction goes forward. When we say enzyme kinetics, what we're doing is that we're studying specifically enzymatic reactions and how fast, again, they go forward. So for any reaction A going to B, there is a velocity, or that's the rate of reaction, which is basically the amount of A disappearing, or that is the rate of A disappearing per unit time or during a period of time, or the rate of appearance of B over a period of time. So it's basically rate of reaction, or V, velocity, delta A or delta B over delta T, change of A or B over change of time during a period of time. Now for chemical reactions, 1 over T is basically constant, but notice the negative sign in here, okay? So for any chemical reaction, 1 over T is constant. So you get what is known as a rate law, which basically says you have a constant for a specific chemical reaction times A. Okay, so the rate law says it describes how concentrations of reactants and how concentrations of reactants affect the rate of reaction. So the more A you have, the faster the reaction. Okay, so the rate is proportional to the concentration of A, and K is a rate constant, and usually A is defined as, or the units of K is 1 over time, a unit of time. Usually it is in second. So right here, for any enzymatic reaction, you look at this plot, you can see that over a period of time, usually again it's in seconds. Here you have number of molecules in the y-axis. You have a gradual increase in B, okay, or similarly you have gradual decrease of A for any chemical reaction. Now, if you look at these, sometimes for reactions, substrates or reactants can affect chemical reactions. And usually, if it's linear, looking like this, so here you have the higher the concentration, the higher the rate is. So you have it something like a linear plot. So the rate of the reaction, the velocity, would be equal to K, again the constant, times the concentration of A. So the higher the A is, the higher the A concentration is, the higher the rate of the reaction is. Now this is known as a first order reaction, okay, because again you have only one factor that affects the rate of the reaction, which is the concentration of A. So you have this linear increase in the rate of the reaction. Now for some other reactions, regardless of how much A you have as a reactant, the rate of the reaction is not affected. Okay, so it's basically a straight constant line that does not differ with by the concentration of A. Now this is known as a zero order reaction because there is nothing that affects the rate of the reaction. Oh, that is in terms of A, that is. Okay. So enzyme kinetics basically deals with enzymatic reactions and how fast or slow they go. So if you look at the plot for an enzymatic reaction, it looks hyperbolic. Now we covered the meaning of this type of plots in the myoglobin slides or lectures. So what it says is that you have in the x-axis you have substrate concentration, and here in the y-axis you have the velocity of the reaction. Now notice how it looks. So basically what it says is that it runs fast at low substrate concentrations, and then it plateaus. So it forms a plateau, okay? And at high substrate concentrations, the rate of the reaction is less affected, and it becomes actually flat at very, very high concentrations of substrate. Okay, so notice that it looks like a first order reaction at low substrate concentration. So it's linear, okay? And then it becomes a zero order at high substrate concentration until it reaches what is known as Vmax, or the maximal velocity of an enzymatic reaction. So why is it the case? Why does it plateau? Well, because at very low substrate concentration, you have a lot of enzymes and minimal concentration of substrate. So the reaction goes really fast because enzymatic reactions are fast overall. So reactions go really fast at low substrate concentration. Now, when you have really high substrate concentration, it plateaus because now enzymes are saturated, and even if you add more substrate, still enzymes are saturated. They just cannot go faster anymore. So the idea here is that at very low concentration of substrate, the rate of the reaction is dependent on substrate concentration. But here, at very high substrate concentration, the rate of the reaction is not dependent on substrate concentration, because no matter how much substrate you add, the reaction rate does not go faster. Rather, now it depends on the enzyme itself and how good the enzyme converts the substrate to products. So it's almost like a road. Okay, so if you have a road there, let's assume that the road is a substrate, okay, and your car is the enzyme. So the idea is that if the road is very narrow and curvy, now in this case, the speed of the car depends on the road. It does not depend on how good your car is, right? So your car would be slow. Now let's say that you make the road wider. So the car would go faster, right? Now let's say that we make the road even wider. Well, now the limiting factor is not the road itself, it's not the substrate, it's really how good your car is in terms of speeding up. So if you make it really, really wide, well, it doesn't matter. The car would still go as fast as it could, because now the limiting factor is not the road itself, right? Now, so again, that's basically what it says. At a fixed concentration of enzyme, okay, the velocity is linearly proportional to the concentration of S when S is small. But then the velocity becomes independent of the substrate when the substrate concentration is very large. And until the enzyme gets to its maximal velocity, or you get to the maximal rate of a reaction, which is Vmax, which is now independent again of the substrate, rather it depends on how good the substrate, how good the enzyme is. So Vmax tells us something about what is known as the turnover number, which is basically the number of substrate molecules converted into a product by an enzyme molecule in a unit time when the enzyme is fully saturated with the substrate. So Vmax tells us something about how good the enzyme is. Okay, so there are two scientists that studied enzyme kinetics, and they came up with an equation, and you need to memorize this equation. It's known as the Michaelis-Menten equation, and it says that the rate of the reaction is equal to Vmax, maximal velocity, times concentration of S over concentration of S plus Km. We will describe Km in a few seconds. So you need to memorize this, okay? So velocity is equal to Vmax, the maximal velocity of an enzymatic reaction, times the concentration of S over the concentration of S substrate plus Km. So what is Km? So Km is related to the substrate concentration when the velocity of the reaction is half of Vmax. Okay, so here you have the maximal velocity. Go 50% of it. That's it. It's this point right here. Go there and go down, and you get to a substrate concentration where, again, velocity is half of Vmax. So the idea here is that when the substrate concentration is much less than Km, this value right here, notice that the velocity would be dependent on both the maximal velocity, okay, over Km times substrate. So the velocity is really dependent on the concentration of the substrate. Now, when V is half of Vmax, then what you have in here is the Km would be equal to the concentration of substrate. So these two are the same. That is double this, of course. So in this case, the velocity would be equal to half of Vmax. Okay, so plug in the numbers. Okay, let's say that substrate concentration is 1, so that's 1 over 1 plus 1, that's 2, so that's half. So the velocity would be half of Vmax. Now when the substrate concentration is very, very high, higher than Km, so we're talking about something like in here, for example, or even more, in this case, this value would be insignificant compared to the concentration of substrate. So let's say that Km is 1, but the substrate concentration is 99. So what you have in here is 99 over 100, which is almost 1. So basically, the velocity of the reaction would be close to Vmax. Now, Km is also known as the Michaelis constant. So it's constant for any specific enzyme. Now, again, so Km is the concentration of substrate when the velocity of the reaction is half of Vmax. Okay, that is, it's the concentration of substrate when 50% of the active sites are filled with a substrate. So it's the same concept as the P50, the pressure of oxygen, when 50% of the oxygen binding sites of myoglobin and hemoglobin are filled with oxygen. Same concept. So the idea here is that Km gives us a measure, it gives us a sense. Okay, so it's not an accurate measure, rather it gives us a sense for the affinity of an enzyme towards a substrate. So the idea is the lower the Km, the higher the affinity. That is, the lower a low Km indicates that you need little substrate to fill 50% of the active sites. Now, if you need high Km value, if you need high substrate concentration to fill 50% of the active sites, it means that the affinity is very low. Okay, so again, the Michaelis constant Km for any reaction E plus S enzymatic reaction, right? You have this complex forming ES complex, and then you have enzyme plus product. The product is released. Remember this equation, we talked about it before. Now, there is a constant value for ES formation. So binding of substrate to enzyme has its own constant, and it's known as K1. Now the reverse is K minus 1. Okay, so it's the opposite of K1. Now there is also a constant for the reaction going from ES to E plus P, and that is known as K2. So Km is basically K of dissociation over K of association, right? So the idea here is that K of association is K1. K of dissociation, well, you have two values. It's either that the substrate would be released or the product would be released, that is K2 in here. So you have the lack of formation of ES. It goes both ways, either to the left or to the right. So Km is equal to K minus 1, this one right here, plus K2, this one right here, over K1. Okay, K rate of dissociation over rate of association. So Km again describes the affinity for the substrate, but it is not an accurate measure of affinity. Why? Because you have K2. K2 does not describe the affinity. Rather, it's K minus 1. But okay. So K minus 1, it can be much higher than K2. Right? Because once you have a substrate bound to an enzyme, the enzymatic reaction is really fast. So the limiting factor really is having the substrate bind to the enzyme. So usually K minus 1 is much higher than K2. So in this case, Km would be equal to, in fact, K minus 1 over K1. Now, and this is known as the dissociation constant. So basically, it's again K dissociation constant is equal to K minus 1 over K1, which is the actual measure of affinity. But Km again gives us again a sense of affinity. So how is a rate of an enzymatic reaction influenced by substrate concentration and Km? At very low substrate concentration, the rate of the reaction is proportional, directly proportional to how much substrate there is in the system, and it's also related to Km. It's affected by Km, how good an enzyme binds to a substrate, right? So it's affected by both. Now at very high substrate concentration, now Km, the effect of Km becomes minimal, right? And no matter how much you increase substrate concentration, the rate of the reaction is not affected. Okay, because this would be almost a value of 1 almost, right? So it really, at very high substrate concentration, it depends on how good the enzyme converts a substrate to a product, because now the limiting factor is not having the enzyme find a substrate. It's the substrate is always there, and the enzymes almost all enzyme molecules are bound to a substrate and so it depends on how good it converts this substrate to a product. Now, Km values of enzymes range widely. So the range is like something 10 to the minus 7 to 10 to the minus 1. Okay, so notice here these are the Km values for different enzymes. Now there's only one substrate for catalase, and it has its own Km value, which is quite different than Km values of hexokinase towards ATP and hexoses. So what does hexokinase do? Hexokinase is an enzyme that phosphorylates hexoses, that is 6-carbon sugars like glucose and fructose. So it binds to ATP at a certain Km value, or it has a certain Km value for ATP. It has a different Km value for glucose, right? Now, and a different Km value for fructose. So there are different Km values for different substrate for the same enzyme. Now, let me explain this further. So let's look at example number 1. So you have the same enzyme, hexokinase, binding to different substrates in one reaction. So you have glucose plus ATP, and the products are glucose 6-phosphate plus ADP plus proton. Now the thing is, for this reaction, Vmax of hexokinase is constant. It's the same. So let's say that we have very high concentration of glucose and we have a range of concentrations of ATP from low to high. So let's look at this red plot right here. So let's say that the limiting factor is not glucose, it's ATP. And you're increasing the concentration of ATP right here. So the more ATP you add, the faster the reaction, right? Until it gets to a point where you get to Vmax. Okay? No matter how much ATP you add, the velocity of the reaction does not change much until you get to Vmax. Let's say that the concentration of ATP is not limiting. You have a lot of ATP in the reaction, and you have different concentrations of glucose. Now, so the more glucose you add, the faster the reaction, right? Until you get to a point where no matter how much glucose you add, there is little change in the rate of the reaction. Eventually, you will get to the same Vmax as when you are changing the concentration of ATP, eventually. But notice that the Km values for this enzyme towards the different substrates is different, right? So, what if you have same enzyme but different substrates in different reactions? So hexokinase can actually phosphorylate glucose, it can phosphorylate fructose, and it can phosphorylate mannose. Okay, so different reactions, different substrates, but we're talking about the same exact enzyme. Does Km differ for this enzyme towards glucose, fructose, and mannose? Definitely it does. So the Km values are different for the different substrates. How about Vmax? Does it differ? And yes, it does. So there are different Vmax values for different substrates, different reactions. Remember, we're talking about different reactions. So look at the Km values. Hexokinase has different Km values for glucose, mannose, and fructose. To which substrate does hexokinase have the highest affinity? And to which substrate it has the lowest affinity? Remember, the higher the Km, the lower the affinity. And the opposite is true. Well, let's look at different enzymes catalyzing or converting the same substrate in different reactions. Okay, so again, we talked about hexokinase. It's the same enzyme right here. Okay, so towards glucose and fructose, different Km values and different Vmax values as well. Well, how about the same substrate right here, fructose, but different enzymes catalyzing a similar reaction. So you have hexokinase, which can phosphorylate hexoses, and you have fructokinase. Now, this enzyme is specific for fructose. It phosphorylates fructose specifically. So we're talking about the same substrate, that is fructose, but different enzymes and different reactions. Do they have different Km values? Definitely they do. Okay, so you can look at these values right here. It's 1.9, okay, versus 1.73. Now, which enzyme has a higher affinity towards fructose? Well, let's look at the Vmax values in here. Again, they're different because we're talking about different reactions. Now, notice here, by the way, you need to pay attention when we compare the first two reactions, the hexokinase reactions, phosphorylating glucose and phosphorylating fructose. Look at the Km values, 1.9, 31.5. But pay attention to the units. Here it's micromolar. Here it's millimolar. So the affinity towards glucose is much higher than its affinity towards fructose. So here's an example. So someone is doing an enzymatic doing measurement of enzymatic reactions, and this person got these values, different substrate concentrations, and here you have the initial velocity. You have the velocity of the reaction. Notice how the more substrate you add, the faster the reaction. Now, the question is, what is Vmax of this reaction? Now, it's 49, 96, 349. It's increasing largely. And then you get to sort of like a plateau. So I can assume that the Vmax of the reaction is around 700 micromoles per minute. Well, how about Km? Well, it's half of 700, about 350, something like this. So Km is about 8 micromolar. So the answer is E. Now, is Km important? Definitely, because it tells us something about enzymatic reactions. So let's say that, let's look at these two examples. What if Km is lower than physiological concentration of S? So we're talking about Km values right here, and the substrate concentration is very high. It just tells us that for this enzymatic reaction, the rate of the reaction, the velocity of the reaction is constant regardless of variations in the concentration of substrate. What if Km is higher than the physiological concentration of S? It means that the rate of the reaction will be greatly varied according to how much substrate there is. It also tells us something about metabolic pathways if we understand a certain Km and Vmax of different reactions. So let's say that you have substrate S, and this S can either be catalyzed by enzyme B converting it to P, or by enzyme A converting it to X. Now, how do you know what the cell decides? Does it want to convert S to P or S to X? Does it want to activate enzyme B or enzyme A? So if you look at the kinetic values or the kinetic plot of this for this substrate and for these two different enzymes, you can notice that the reaction goes really fast when the substrate concentration is very low. The reaction catalyzed by A is favored, right? Because at this concentration, here's the rate of the reaction for enzyme B, and that's the rate of the reaction for enzyme A. So when the substrate concentration is very low, this reaction S to X is favored. But when the substrate concentration is very high, then in this case, it's the other reaction that is favored. The reaction catalyzed by B goes much faster than the reaction catalyzed by enzyme A. So look at this plot and try to answer these questions. I think I did, but try to interpret what happens at different concentrations of S. Now, there are different uses for Km. So basically, it tells us about substrate preferences of an enzyme. Let's say that there are two substrates for the same enzyme, two Km values. It tells us something about what substrate an enzyme favors at different concentrations of each one of them. It can distinguish isozymes. We'll talk about these isozymes in the regulation lectures next week, inshallah. So it tells us something about isozymes. Now, isozymes are different enzymes that catalyze the same reaction. So different enzymes catalyzing the same reaction. Now, these enzymes may differ in having different Km values for the same substrate. So Km tells us something about the preferences of different isozymes for a single substrate. It also tells us something about abnormalities in an enzyme. If we notice that there's a change in Km values of an enzyme towards a certain substrate, it tells us that probably this enzyme is mutated. So what is the effect of enzyme concentration of Vmax? So we talked about Km, right? So let's talk about Vmax right now. Now the idea here is that the higher the enzyme concentration, the faster the rate of the reaction. It makes sense, right? So the more enzymes you have, the faster the reaction. So let's say that you have a different concentration of enzymes for a certain substrate. Now the idea here is that the Vmax would differ as well, depending on the concentration of the enzyme. So if you double the concentration of enzyme, you also double Vmax. Well, let's put things together. For an enzymatic reaction, E plus S forming ES complex, again you have rate constants in here, K1, K minus 1, and then ES is converted to E plus P, okay? And there is another rate constant for this reaction as well. Now, the maximal rate is equal to the product of K2. And K2 is also known as Kcat, or the catalytic efficiency, the catalytic constant of an enzyme, because each enzyme has its own efficiency, right? Catalytic efficiency. And so Vmax would be related to its efficiency, the efficiency of the enzyme, as well as the total concentration of the enzyme, right? Because Vmax differs according to the concentration of the enzyme, but its catalytic efficiency is the same. So Vmax would be equal to K2 times the concentration of a substrate. Now, or Kcat would be equal to Vmax, right, divided by the concentration of an enzyme. Okay. Now, so Kcat is constant given for any given substrate. So KCAT gives us something about the efficiency of the enzyme, how good the enzyme is in converting ES to E plus P. And these are different catalytic constants for different enzymes. Now notice here, for catalase, it's 40 million per second. So these are the units for KCAT. What does that mean? Well, flip this number. What this tells us is that a single enzyme, a single catalase enzyme, can catalyze 40 million reactions per second. Carbonic anhydrase, it can convert 400,000 substrates into carbonic acid per second. This is huge if you think about it. A single molecule, a single enzyme can convert 40 million, it can catalyze 40 million reactions per second. Catalase, in fact, is one of the most efficient enzymes that exist in nature. KCAT is equal to Vmax over the concentration of an enzyme. So in words, KCAT is basically the turnover number. It's the concentration of substrate molecules converted into a product per unit time. That's Vmax per concentration or moles of an enzyme. That is when the enzyme is fully saturated. Okay, so it describes how quickly an enzyme acts. It's really K2. It's how efficient the enzyme is in converting ES to E plus product. So we have to know the concentration of enzyme in order to know what KCAT is. So here's an example right here. So you have a certain enzyme and it has a molecular weight of 50,000 grams per mole. You use 10 microgram of the enzyme in an experiment and results show that the enzyme at best converts 9.6 micromoles of the substrate per minute. At best now means Vmax. So the turnover number of the enzyme is, so do the calculation. Now remember that moles is equal to grams over molecular weight of the enzyme. So you can calculate the moles of an enzyme. You have the amount in grams over, that's the molecular weight. So you can calculate Vmax. So I'll give you 2 seconds to think about it. And here's the solution. So you have the molecular weight, you have the weight, and you have Vmax. So KCAT is basically 9.6, that is Vmax, over 60, because we're doing it in seconds, okay? Divided by moles of an enzyme, how much enzyme you have, which is 10 micrograms per 50,000. Be careful of the units, okay? So here's another problem right here. So when you calculate KCAT, you can flip the numbers and it tells you the time it takes for a reaction to take place, okay? So again, if you flip the number, it tells you, so this KCAT means number of reactions per second or number of molecules converted per second, okay, which is, again, it's really amazing. So KCAT tells us something about how good an enzyme is in converting a substrate to a product once it binds to it. But it does not give us any information of the affinity, how strongly it binds to the substrate. At the same time, Km tells us something about the affinity, but it does not tell us how good an enzyme is in converting a substrate to a product um, once it binds to it. So it's really the combination of both Kcat and Km that can give us information about how efficient enzymes are. So the higher Kcat, the better the enzyme is. And the lower the Km, that is the higher the affinity, the better the enzyme is. Okay, so you need both combinations in here. So, um, so the efficiency of an enzyme can be determined by taking Kcat over Km value. Okay, so let's look at some enzymes in here. We have catalase. Catalase, I told you that it is one of the most efficient enzymes in nature. It converts 40 million molecules into a product per second, which is amazing. Now, but look at Km. It's quite high, isn't it? So the enzyme is efficient, but it doesn't bind strongly to the substrate. Well, let's look at lysozyme. Lysozyme has poor Kcat, but its affinity is not bad, right? So compare Kcat to and Km of different enzymes. Let's look at some terms right now. So we have the rate of reaction, or Vmax, which is basically the concentration of substrate disappearing or product appearing per unit time. That's Vmax, right? So it's moles, per liter per second. Okay, that is molarity in other words. Okay, so molarity is equal to moles per volume. So that's rate of reaction. Now, if we eliminate the volume from this equation, we would get what is known as enzyme activity, which is basically it's the number of substrate molecules disappearing or products appearing per unit time. Okay, that is moles per second, regardless of the volume. So that's enzyme activity. So it's rate of reaction, velocity, times reaction volume, and we would get enzyme activity. And we have specific activity. Now, specific activity is used to measure enzyme purity. So let's say that you have a solution of an enzyme and maybe there are some contaminants. Now, if you measure moles of substrate converted per unit time per unit mass of enzyme, that is the weight of that solution or powder or whatever, it tells us something about the purity of that solution, because if it contains other things, they would contribute to the weight, right? And the specific activity would be lower. But if the enzyme is pure, we would get its own constant specific activity, because now each enzyme has its own specific activity at in certain conditions. Okay, so in the same condition, so the specific activity would not change at the same conditions, but the experiment or the assay or the activity is measured at a different time point, so it's constant. Okay, under the same conditions. So specific activity is basically moles of substrate converted per unit time per unit mass of an enzyme. Okay, so it's enzyme activity divided by mass of an enzyme. Now remember, in order to calculate Kcat, not only that you need to know what Bmax is, but you also need to know what the concentration of the enzyme is, moles or in molarity of the enzyme. Now, then you get to turnover number, which is basically specific activity of the enzyme times the molecular weight of the enzyme. Now, in this case, it is expressed as moles of substrate converted per unit time, and usually it's per second, per moles of an enzyme, per 1 mole of an enzyme. So it's per second or per minute. Okay, so that's the turnover number. So you can calculate Kcat starting from all of these variables. So here's a problem that combines all of these terms that we've just talked about. So you have a solution containing 25 times 10 to the minus fourth molarity of peptide substrate. So now we have the concentration of the substrate. And you have 1.5 micrograms of chymotrypsin, that's the enzyme, okay, in 2.5 mils. And the molecular weight of the enzyme is 25,000, okay, so you can calculate the molarity of the enzyme. Now, after 10 minutes, the velocity of the reaction is 18.6 times 10 to the minus fourth of peptide substrate remaining. So you need to calculate the velocity of the reaction. So it's basically, so the velocity of the reaction, the rate of the reaction, is how much substrate consumed per unit time, which is 6.4 times 10 to the minus 4. That is because you're starting with 25, and after 10 minutes you end up with 18.6, right? So the amount of substrate converted is 6.4 times 10 to the minus 4th in 10 minutes. Okay, so this is the rate of the reaction. Now, enzyme activity is rate times volume. Well, we know what the volume is, which is 2.5 times 10 to the minus 3. Now, please pay attention to the units. This is milliliter, and it needs to be done in liters. So the enzyme activity in this case is the rate of the reaction, okay? That is 1.6 times 10 to the minus 4th, okay? Sorry, it's 6.4 times 10 to the minus 5th times the volume, which is 2.5 times 10 to the minus 3, and that's enzyme activity. Now, we need to know the specific activity of the enzyme. That is, we know we know the amount of enzyme in micrograms. Again, specific activity tells us something of the purity of the enzyme. So it's basically the activity of the enzyme over the grams of enzyme, how much enzyme you have, which is in this case 1.1 times 10 to the minus 7th. Okay. Now the turnover number. Now you need to multiply specific activity by the molecular mass, and you already have it in here, and that tells us something about the turnover number. So basically, one enzyme catalyzes a reaction catalyzes 45 reactions per second. Now, there's a problem with the Michaelis-Menten equation, and there's a problem with the Michaelis-Menten plot. And that is, notice that the hyperbolic line, never gets to Vmax. Because realistically, it's impossible to have that much substrate to calculate Vmax. And since we cannot determine what Vmax is, we would not be able to tell what Km is. And as a result, we would not be able to calculate the rate of any reaction at any substrate concentration, because we need both. Now, the only way by which we can do this is if we convert the Michaelis-Menten equation into another one that gives us a linear plot that looks like this. Okay, and this is how the equation should look like. Y, that is the rate of the reaction, equals mx. X is the substrate concentration in this case. That's the x-axis, plus b. Now, b is the y-intercept, the point where the line hits the y-axis, and m is the slope. Now, this has been done by two scientists known as Lineweaver-Berg. And they drew this plot right here that is also known as the double reciprocal plot. Now, this is the equation, okay? So it's 1 over V equals, and now I don't care about the derivation of this equation. So it's 1 divided by V equals 1 over Vmax plus Km over Vmax times 1 over S. Okay, so this is the linear equation that I just told you about. Now, so the idea here is that this point right here, now, so you can do an enzymatic reaction, you can do a measurement of an enzymatic reaction, rate of an enzymatic reaction, and you can collect these points right here. And then you can draw this line, and this line is hypothetical because you would not be able to get substrate concentration in negative values, right? Okay, and you would not be able to have a rate of a reaction in the absence of any substrate, right? So it's all hypothetical, but these are real. Now, this point right here, the intercept is actually the value of 1 over Vmax. And this point right here, this x-intercept, is minus 1 over Km. Okay? So you can really do an assay, and you can extend the line, and you would be able to calculate Km and Vmax. Now the slope is Km over Vmax. This is M right here. Okay, so that's X. 1 over S is X. Km over Vmax is M, the slope, right? This is B, and 1 over V is the velocity of the reaction, the Y. Great. So you need to memorize this equation as well. So if you have, Y is y-axis, 1 over V, X is the x-axis, 1 over S, M is the slope, we already mentioned that, and B is 1 over Vmax, okay? So it follows this linear equation right here. If X is 0, so we are at this point right here. If X is 0, it means that this whole value is 0, right? Again, hypothetically. It means that 1 over V would be equal to 1 over Vmax. So this point right here actually represents 1 over Vmax, the value of 1 over Vmax. What if Y? So let's say that this point right here, the intercept, the y-intercept is 10. So what is Vmax? If this is 10, that represents 1 over Vmax. It means that Vmax is 0.1. Let's say that this point right here is minus 10. Now remember that minus 10 is equal to minus 1 over Km, so you can remove the negative sign. Okay, so 1 over Km is equal to 10, so Km is 0.1. So you need to flip it.